Recording. Looks like we've got a reasonably healthy turnout already here, so I may as well go ahead and get rolling. Excuse me. You may not have even seen the email yet. I had just posted a couple alternative solutions to the homework I posed on last Wednesday here. So if you haven't already, you may want to take a look at that. But we'll step through it here. So I suppose that could wait until we're done. So let's remind you where we were going to go today. Where we are. Okay, so we were looking at, bring this up here. Okay, so we were looking at an example here of the effect of topiramate on the number of migraine days per month. The idea being, of course, to use topiramate to try and reduce the migraine frequency. So the data that we have here is I've got some published data from 7 trials where we're looking at the number of migraine days per month versus dose. In here, these are endpoint data. Some of the studies do vary somewhat in duration, but again, it's been normalized to days per month in the way this is presented here. Just remind you how a migraine day is defined is it's any calendar day during which a patient had a migraine headache, basically, with the further qualification is usually that it be at least 30 minutes, though I think that part of the definition may have varied a bit from trial to trial. Excuse me, I sound a little gravelly this morning, or this afternoon, I guess. So, and I had showed one approach to modeling that where I treated the migraine events in terms of counts and used a Poisson-based model. And in particular, the number of accounts, the counts that we're talking about here, since we're working with summary data rather than individual data, is I did it in terms of the total number of migraine days in the eye treatment arm of a given study. So we're actually taking so I start out where, in this case, the lambda ij is the reported mean number of migraine days per month. In here, I multiply that by n here, the number of patients in there, and then further multiply that by whatever the observation period was, whatever that duration is, to get an estimate of the total counts for that particular treatment arm, and modeled that in terms of a Poisson distribution. And that goes back to that notion that if the counts within the individuals are Poisson distributed, then the sum of those Poisson distributed counts, it would also be Poisson distributed. So I'm basically then just counting up the total number across all the patients and modeling that in terms of Poisson. And we did that. It was certainly a less than optimal model, but it just illustrated the use of that particular approach. And suggested that perhaps you go off and take a shot at trying to improve upon that non-optimal preliminary model, but while still retaining the idea of modeling event counts as discrete random variables. And then also implementing a model where we just use a normal likelihood instead, rather than try to model this as a discrete random variable, and to take a look at a comparison of the results. So where I'm at on that is, I suppose that was actually homework for me too, because I hadn't done that. This was kind of an extemporaneous homework assignment. And I actually won't claim to have come up with any major improvements here. And in particular, I haven't really optimized the models I've worked with, but I'll show you an example going in both directions here that could almost certainly be improved upon. In fact, I've got some head scratching to do about the results for one of them, which I'll show you in a minute. So let's go ahead and jump into the first one, this idea of let's take where I started there, but let's see if we can improve upon that but still be treating these event counts as discrete random variables. Now I also alluded to the notion last week where now, though I used the Poisson distribution in this initial model, I realized after thinking about it that you could argue that that might not be uh, the model which is really most consistent with the underlying situation. Generally, you use a Poisson distribution in cases where uh, the, the the counts of the events are such that you could have, at least theoretically, an infinite number of events within any given interval. Um, and with the context we have here, that really isn't the case because we're only counting up the number of days in which an event occurred, as opposed to necessarily counting the number of events. And of course, with any given trial, there's a finite number of days. And so you don't have a situation where this random variable could be a, potentially, you know, potentially infinite number of counts in this case, because it's restricted to that. And under those circumstances, you could argue that, gee, maybe the more appropriate model would be to use, say, perhaps a binomial model, where you talk in terms of the probability of an event occurring on any given day, and then you apply that probability over all the days within the trial, and the number of days that you have a migraine event could be described then as binomial with some probability for one of the parameters, and the other parameter is just the total number of possible days during which a migraine could have occurred in here. So that's one thing that we might want to consider changing. Another thing which I haven't attempted here is to also allow for the possibility that perhaps the hazard for an event, or I suppose if we're thinking in terms of binomial here, the probability of an event occurring in a day may not be constant over time. That might change here too. For the time being, I didn't attempt to address that in these trials, particularly since I was only looking at endpoint data rather than looking at data over, say, different multiple intervals within a trial. If we brought in a covariate, the best I could have done in this case might have been to bring in a covariate for the duration of the trial, but I haven't attempted that at this point. So let's take a look at one approach. I didn't actually write up any slides for it, so I'll have to sort of talk you through the model just using the BUGS code in here, but let's go ahead and do it. The first approach I did is to sort of take what I had done before using the Poisson distribution and instead going after it with a binomial distribution. The other thing I did is it became pretty apparent that there were some difficulties that might have been related to perhaps trying to throw more random effects at it than the data would support. So I ended up with a simpler model. I actually tried a number of variations on that. You can sort of see like migraine example 2, 3, 4, and so on. The one I'll show you I've got labeled as migraine 6. Again, this is one of the ones I posted on the website for you. Let's go ahead and open that up. Okay. Let's make this a little bigger. Okay, so there's a couple of things here that, well, the first thing, just the basic idea here is, so now what I've got termed as our dependent variable here, the migraine, is is going to be passed in from our R script and as part of the data. And this is going to be the total number of migraine days for a given treatment arm within a study. So again, this is taking the reported mean number, and of course they've generally been reported as a mean number per month, multiplying it by, essentially the number, the duration of the trial, as well as by the number of patients to get a total count of migraine days, and modeling that as a binomial distribution where P is going to represent the probability of a migraine occurring in any single day. And in this case, I'm assuming that that is the same over time, but it will be a function of, well, a couple of covariates. In particular, it's going to be a function of the baseline migraine rate and the dose of topiramate. And again, we've got the other parameter in our binomial distribution is just the total number of days. So the n days then here, in fact, you can see that right here. That's going to be the duration of the trial observation period, which I had passed as data called DT, times the number of patients in that treatment arm, times, also put it as times 28 because DT in the data was originally done in terms of months. Okay. And then the issue is, okay, how are we going to model probability as a function of our independent variables here? Well, there's a couple of things going on. The way I approach this is to get at the probability was to start in terms of thinking of hazard as we do when we talk about time to event models. It's also closely related to the Poisson model. The hazard is essentially equivalent to the, it's closely, I won't say it's not the mean rate, but it's closely related to that. So I modeled the hazard essentially using a Cox regression style model. So I've got the log of the hazard. In this case, I modeled as a linear function of the log of the baseline rate and the dose. So you can see here we've got an intercept component which has intertrial variation in it. You can see the trial specific values of this intercept here are generated in this other loop here, which loops over the various trials, only 7 trials in this case. And then I've got, and that's the only random effect in this case, or intertrial random effect here. Then I've got another coefficient multiplying the log of the baseline rate. That's what this lambda 0 was. If you prefer, you can think of that. That's the by baseline rate is typically in these trials. It was 1 month before treatment was assigned where they counted up the number of migraine days. The division by 6 here is basically, so we're talking about, you can think of that as being centering around the log of the sort of a typical value of the log of that rate. So this is equivalent to saying log of lambda 0 minus the log of 6. So that when you do that, you can think of this intercept here as sort of being the, that would be an estimate of the log of the hazard for a trial in which the baseline hazard was 6. And then finally, just a linear effective dose here on the hazard. And to get the probability, we end up just going, the probability would equal 1 minus e to, well, it's actually e to the minus hazard times the duration of time of interest. I didn't bother putting the multiplication there because the time of interest here is going to be 1 day, and and the way we're doing this is we're setting it up so that the hazard has units of reciprocal days in here, so I didn't really need to do that. So this, again, this probability is the probability of having a migraine within 1 day, so I can just make it 1 minus e to the minus the hazard in this case. So And that's what ultimately appears up here then in our binomial model over here. So that's really the core of the model. We've got one random effect, and in part that's because I had tried this with up to 3 random effects, and ended up with something of a mess when trying to incorporate that many. I suspect that's in part due to, one, we're only dealing with endpoint data, two, we're only dealing with 7 trials here. So I think we just didn't have rich enough data to support that kind of that many random effects in the model. What else to say about the model here? We've got our usual individual prediction here, a conditional prediction. So this would be a prediction of the migraine count for essentially it's predictions for the for sort of new events within the same trial. So it still uses the trial-specific random effect. And then down here we have our population predictions, where this would be, you can think of this as predicting into a potential new trial. Priors on this I made quite weakly informative in this case. Unlike the Poisson case when we tried to run it with such weakly informative priors, I don't run into any overflow problems with this. So it's a little more robust in that sense. So let's take a look at what we get out of this. At least one aspect sort of surprised me, and I still haven't quite decided what's happening, but let's take a peek. Okay, so one of the things that jumps out, by the way, this was, I didn't look at the R. In fact, maybe we should, before I even go through this too far, take a quick look at the R script that goes with it. Most of this is very familiar. Just point out that to get the original data set had the monthly migraine rate. In other words, it had the what was contained in it that is called migraine rate here is the number of migraine events per month. So the one thing that's happening in the data component here is I'm converting that to the total number of migraine events in the treatment arm. So I'm taking the monthly rate times the number of patients times the where are we going here, times the end time and start time. In this case, we're in weeks in the data set, so it's calculating that in weeks and then dividing by 4 to get it in terms of months. Here I'm just using 28-day months, which is actually consistent the way the large majority of migraine trials are done. What they call a month is actually a 28-day month. So I'm doing that. So that's getting that total count. Similarly, what I'm calling DT here, I've converted that to number of months in this case too. Not much else, a bunch of initial estimates. After that, it's all pretty conventional. So let's take a look at the results of that. One thing that jumps out is this A mean 2. So that is the coefficient multiplying, double check here, but I believe that's the one multiplying baseline. Yes, it is. And for some reason, we've got a problem here. And what I've done so far, I would have run this longer, but I was running out of time. You can see that there's strong autocorrelation plus a general trend, it looks like. So we've got some issues here as far as both convergence and any mixing here. So we'd certainly have to run this a whole lot longer if we were going to leave the model as is before we go further. That was one surprise. I thought when I simpled this out that was not likely to happen, but I guess well, not much to say about it other than the fact it is something of a problem here that would need to be resolved before we'd have a suitable production run. not much to say there. So anything we look at here, we kind of have to look at, sorry, jumping around too much. We have to look at with a bit of a grain of salt here, because this is almost certainly something we can improve upon, um, either by changing the model structure. I suspect that might not even be entirely necessary, as much as maybe doing some reparameterization. But I haven't quite decided what it would take to accomplish that yet. So you get to see the problems. And when I look at this, by the way, nothing jumps out as the source of the problem. One of the reasons I'll often do this kind of a pairs plot, where I'm plotting the MCMC samples of each parameter against the other. In here, I'm looking for any really strong correlations that might induce some of that autocorrelation, and nothing's actually jumping out in this case. And then this is actually the part that was more of a surprise than the autocorrelation problem, which I've run into before, and sometimes you just have to struggle until you can find a better parameterization. But what surprised me here is what is a suggestion of some overfitting. We've obviously done a generally pretty good job of, these are the individual predictions now, and most of them, uh, are most of the predictions are very close to the observed data. But what's particularly striking to me is the extremely narrow prediction intervals or credible intervals here. And I haven't diagnosed why that is the case, and I'm surprised that one random variable in this, which varies by study, not by treatment arm, was sufficient to narrow it down that much. So anyway, that's something of an open question at the moment as to what the heck's going on there. And then this is the population predictions, which is a little more consistent with what I might have expected. There's obviously, when we're no longer looking at random effects conditioned on the specific results of a given trial, we see much broader credible intervals here. They generally run more or less along the lines of the observed data, though there's some hints of some, um, of some systematic errors or deviations in here. You can see that, by the way, keep in mind, the only reason within uh, within a, not a treatment arm, but within a dose group, that you see differences here is because we have another covariate here, namely the baseline rate. And so the reason why you see differences in the posterior predictions within a dose group is because you're looking at cases where the baseline rate is different. And in general, the higher probably the easiest thing to spot is the medians here, the red bars. The reason these red bars, for instance, are higher than the ones down here is because they correspond to trials that had higher baseline rates in here. But there is a tendency here to maybe over predict some of the cases where those baseline rate, over predict the cases where we have fairly high rates and under predict the ones where they're lower, suggesting that we may want to use a different functional form than what we've got here. This, by the way, was one diagnostic here. I was trying to figure out why we were getting such narrow predictions for the individual predictions, and this is I should have actually changed the label. What I'm actually looking at here is the posterior distribution of those probabilities. Actually, it's the probabilities multiplied by the sample size to see if that made a difference. And not only didn't it make a difference, it made things even narrower. So anyway, there's some question marks here that I'm trying to resolve. But so the main lesson I would take away from this, though, is just the notion that you could model this in terms of a binomial, but that there's definitely some issues with this specific implementation that are as yet unresolved. In fact, I'm still trying to figure out if I did something in the way of an error in coding it, but I've gone through that a few times and don't think that's the issue, but I could be surprised. So before I go to the next approach on here, any questions, or if you like suggestions on this one? Oops. There we go. Okay, the question, would different priors help? Since I use such weakly informative priors, I don't think so. And so, usually what I would expect is that if I'm seeing problems in terms of getting what appears to be overfitting, using stronger priors, if anything. Well, it depends. If I use strong priors that are inconsistent with the data, then I suppose that might do something strange, but it wouldn't necessarily be a beneficial change. So it might be curious to see how sensitive this is to the priors, but I doubt that the width of these credible intervals would be strongly influenced by it. Again, unless I pick some particularly strange priors that are actually kind of inconsistent with the data. Okay, why don't I go ahead and do the next approach here, where I had suggested, what if we just said, okay, instead of going through this extra effort to try and describe the data as discrete, and granted, it under the hood it is discrete data, but in the end, the way we actually are getting the data is no longer in its sort of original raw discrete state from each individual patient. We're now getting data as mean counts or mean number of days over, a usually fairly sizable patient populations here. So yes, technically there's still some, the data is still sort of discrete under the hood, but we also know that means, in at least in the limit, should be something we might be able to approximate. Well, as the sample sizes get larger and larger, those means are more closely approximated as normal distributions. So maybe we should just take a shot at just describing this data as normal, particularly in cases where the counts are sufficiently high that it's not like we're talking about trying to do counts of 1, 2, and 3. We're generally running a bit higher. So these things might be approximatable as sort of continuous. And again, a normal distribution might be applicable. So let's take a look at an approach for that. And there I used a very simple strategy here. Again, I just went linear as a first shot at it. Here we go. That's number 7. Here we go. So I went real simple on this one. Again, I stuck with only one random effect in this case and associated it with an intercept of a linear model. And this one is a pretty direct linear. There's no playing games with trying to estimate a hazard and converting that to a probability and so on. I just went directly to describing the mean as a linear function, very simple one. It's just an intercept with a component, multiplying our baseline migraine rate, and another component multiplying dose. At this point, I didn't attempt, and it might make sense to also attempt an interaction term. I haven't done that at this point. But again, I just started out with about as simple a model as you can imagine that incorporates both dose, the baseline, and at least some intertrial random effect as part of it. And so we've got that. So that's describing our mean, which appears as a mean inside of our normal likelihood. We've got our residual variation here, which is adjusted for sample size, right down here where sigma represents the residual standard deviation. So we're just taking n over sigma squared for our precision. So that's pretty much all there is to it. Not a whole lot. Let's see, is there anything down here to be said? Not really. Again, pretty weakly informative priors for what we're working with here, there, as well as our coefficient terms here. And yeah, not much to be said about that. It's a very simple, normal, it's basically a typical linear mixed effects model here. Something we could have run with, with a number of tools, including like, we could have used LME inside R, or could have used, I'm forgetting what the name of the proc is, proc mixed in SAS or what have you, except that I guess it wouldn't be Bayesian, but in this case, we're not really making much, taking much benefit from the Bayesian machinery. So we'll go ahead and run that. This one, by the way, runs very quickly because BUGS will recognizes that we do end up with some conjugate systems in here that allows it to do a lot of the sampling sort of semi-analytically as part of this. So it actually runs pretty quick. I took advantage of that and ran a pretty large number of samples. So not much to be said here. Just point out, notice here, I'm no longer doing that calculation to get the total number of counts. I'm just taking the monthly rate now directly as the dependent variable here. Not much to be said about the initial estimates. These actually I haven't gone back to see how good or bad they were because these I just eyeballed for the most part from the data in here, and you can see I ran 100,000 iterations per chain, tossing away the first 20,000 of each and just keeping every 50th of the remainder. And when you do that, you get something moderately clean. You see a couple of odd little blips in a couple of these, but nothing too gruesome on it. I think that's pretty much all the parameters that we're looking at here. Oh yeah, there's this guy. This one I do see that we actually have some pretty strong correlation between this A-min1 and A-min2. We might have been able to reduce that. In this case, I did not center the covariate. So for example, for the baseline, if you recall the model, we go here, I did not, in this, unlike what I had done for the binomial model, I hadn't centered around any sort of middle ground or, value for our migraine rates. If I had maybe centered this around something like 6, something near the mean migraine rate that we see there, that might have reduced that. That'd be something you could explore, for example. And that might improve the MCMC performance a little bit. But again, since this runs so quickly, you can pretty much brute force it and not have to agonize too much over that. Now this is the individual predictions now, which you can see are they do a fairly good job in terms of predicting the individual effects. I haven't looked real carefully in a critical way at this to see if there are any hints of things that I might want to improve on it. But overall, it looks fairly well. But notice that the credible intervals are substantially broader than they were with the individual predictions for the binomial model. Thus, I'm still scratching my head about that, the binomial model, as to why that's the case. Uh, so so generally it seems to be doing a reasonably good job. Here it looks like, gee, maybe we're under predicting there, but on the other hand, another relatively extreme value is over predicted. So the net result is that perhaps we don't have any real strong systematic problems here looking over this. The population predictions, on the other hand, are somewhat comparable and maybe better overall than what we saw with that binomial model. And here they're generally fairly reasonable in terms of picking up the general trends here. Again, that's a pretty subjective view at this point. I haven't looked at it that critically yet. Let's see, I'm trying to think if there was much more to be said about what do we got for parameters here. Well, first of all, the effective ends are generally pretty good. We might even want to push it a little further given what we saw with a mean 1 or 2, or again, do the suggested parameterization of perhaps centering at least the baseline parameter as a way to maybe improve upon that. Let's see. Another question from you, Mike. What do we got? So you said, do I generally add a random effect to sigma or go with what the data is telling you? Part of that's going to depend a bit upon, well, I guess if I just look at the or part of this here, to some degree, I'm going to be dealing with what the data is telling me. In production work, if the data appears to be rich enough to support a random effect on sigma, and by that I'm assuming what you're asking is you're talking about an intertrial, put some intertrial variation on that residual variance term, and if I would tend to attempt that. Usually the early models, when I'm first doing exploration, I don't generally incorporate it, but somewhere along the line I'm likely to attempt putting some intertrial variation upon the residual variation component there to see if that improves the model in any way, and make a judgment call at that point. So I'm not sure if that quite answers your question, but it tends to be a data-driven choice. I was just trying to see if there was any stories to be told around the parameters. I mean, we can see, what do we got here? Did I pull up the right one? Yes. This is a little bit fuzzy to interpret because we don't have anything that really directly represents like a mean count in here. To get sort of an estimate of a mean count, you'd probably have to pull in at least one of the covariates here. So, for example, here we've got the a mean 2 is the thing that multiplies the baseline. So if you wanted to, say, get an estimate of, say, what would be a typical count for let's say a trial with a baseline count of 6 migraines per month in here, I mean, you'd have to kind of take both this your intercept here plus that a mean 2 and multiply it by whatever that would be, say like the 6, so that tells you what your expectations would be under this model, as you'd expect a posterior median here of around 4 for a treatment arm where you had a baseline of 6, suggesting, I guess, that you're still predicting at least some benefit, some reduction from baseline, even in the case of a placebo treatment. In here, and then of course you can incorporate your drug component here. That looks like a mighty small number, but keep in mind it's being multiplied by things on the order of 100 in this case. So if you then wanted to say, well, what if I also had was taking 100 milligrams of topiramate daily, then you would expect something like that. What do we got? That plus this, and again, we'll assume, let's say, a baseline of 6 plus this times that 100. Oh, except I forgot I needed to put a minus on that. Oh, no, it's already a minus. Never mind. So not much of a reduction is what it's predicting. And that's fairly, actually, where's my slides here? Let's see if those are still open. Just to take us back to the picture, you can see here that though we see for most of these trials some indication of benefit with treatment, we're seeing relatively modest benefits as we go from our for placebo down to 100. Though I might have guessed it was slightly more than that. Anyway. See, I see another. Oh, okay, just an okay. That helps. Okay. Trying to think if there was anything else around this that I wanted to tell. I mean, we talked a little bit about things I would want to explore. I'm still scratching my head again as to why the posterior predictions are so narrow in the case of the binomial model. That's not immediately obvious, and it has me wondering about, are we dealing with a coding error, quirks of, is it really a true result, a true posterior under the model? I'm not sure, but one of the things I would be tempted to do would be to attempt another piece of software, such as I'm going to forget the. Oh no, I remember the name. I know Andrew Gelman had been complaining about the performance of bugs on a number of generalized linear models that he had been working with, and worked with some others to develop a new package called STAN, S-T-A-N. I don't think I've mentioned that in the course of this course, but it seems to have some nice operating characteristics for those sorts of models. So one of the first things I would do if I was working with this in a production context would be to take it and implement it in STAN to see if I get comparable results. In other words, is this a characteristic of the model, or am I looking at some quirks of WinBUGs? I'm hesitant to think it's quirks of WinBUGs in this case, but at least I have a fairly high confidence for this type of a model that STAN would probably converge more rapidly and more efficiently than WinBUGs would for this type of a model. So that's one thing I would consider doing. STAN, by the way, is a package that's probably worth looking at. It's, it hasn't been around very long. It hasn't been as extensively explored and tested as WinBUGs at this point, but it does look like it has some interesting properties that might make it something worth having in your toolbox. So where was I going? Okay, so that's something I would want to explore. As I mentioned, in this particular model, I'd probably entertain reparameterizing it so that I centered at least the baseline covariate as part of this and bring it in. Chances are, given what I've seen here so far and the nature of the data, I'd probably be perfectly happy with working with the model based upon the normal likelihood rather than jumping through various hoops to insist on describing the data as discrete in this particular case. Because keep in mind, when we've been calculating out these total number of events for a given treatment arm, we're talking about, actually I haven't even looked at what the raw numbers are, but I'm presuming we're talking about hundreds of events. And once you start talking in terms of hundreds, all of a sudden, whether you treat something as discrete or approximated as continuous starts getting a lot less important. Other things I might do is I did not carefully structure the normally distributed model in such a way to avoid the possibility of ending up with things like negative predictions, because I just used an additive normal on here on the counts. One might make the argument that I probably ought to do something to restrict restrict the model so that it isn't possible to get negative counts when you simulate from the model, and I haven't attempted that at this point. Okay, that's probably about all I've got so far. I'm still, I apologize, I still haven't gotten the midterm out to you. I think I've just about got it whipped into shape. So I should be able to get it to you before this Wednesday's lecture. So I'll go ahead and post that. I think I originally in the lecture notes said that you'd have a week to do it. I think what I'll do is actually give you 2 weeks to complete that. So it'll probably be posted then sometime either tomorrow or Wednesday. So I guess that's pretty much it. Any additional questions or comments? Okay, so far it doesn't look like anything's popping up here, so I guess I'll say farewell till Wednesday. I'll talk to you then.